Have you ever looked at an exam paper and wondered, what are they actually looking for here? Well, today we're going to find out. We are taking a real GCSE chemistry question and we are going to deconstruct it piece by piece using the official mark scheme to see exactly how you earn every single mark. So let's dive in.
So, here's our game plan. First, we'll deconstruct the question itself. Then we'll get into the nitty-gritty of ammonia's structure and bonding. After that, we'll crunch the numbers on energy change, see what that looks like on a graph, and finally, we'll wrap up with the final marks and the most important takeaways. It's the full picture from A to Z.
All right, let's get into it. We are tackling question 05 from a past AQA paper. Now, I want you to think of this not just as a question, but as a puzzle. And our job today is to find every single piece and click it into place perfectly.
And you know, this is why question 05 is such a fantastic case study. It's not just testing one little thing. It cleverly pulls together covalent bonding, physical properties, some serious energy calculations, and even reaction profiles. It's a great example of how all these different chemistry topics are actually connected.
Okay, time to tackle the first few pieces of our puzzle. We're starting with the real fundamentals, the structure and the bonding of the ammonia molecule itself. Here we go, question 05.1, a classic dot and cross diagram worth 2 marks. They've given us the basic setup, and we just need to fill in those outer shell electrons for 1 nitrogen atom and 3 hydrogen atoms. So, where do the 2 marks come from? Let's check the mark scheme. You get your first mark for correctly drawing the 3 shared pairs of electrons, the ones that form the covalent bonds between the nitrogen and each hydrogen. The second mark? That comes from showing the lone pair, those 2 electrons on the nitrogen's outer shell that aren't involved in bonding. Simple as that.
All right, next up. For 1 mark, question 05.2 wants us to think a little deeper about the model we just drew. It's useful, for sure, but what can it show us?
And the mark scheme is crystal clear on this one. To get the mark, you need to say that the dot and cross diagram is a 2D model. It doesn't show the molecule's actual 3-dimensional shape. For ammonia, that's a trigonal pyramidal structure. Think of it like this. The diagram is just a flat map of a 3D object. Now, we've got a 3-mark explanation question. You see these all the time, and they need a really logical step-by-step answer. We have to explain ammonia's low boiling point by talking about its structure and bonding. And here it is, the perfect 3-mark answer, laid out just how an examiner wants to see it. Mark number 1, you state that ammonia has a simple molecular structure, or that it's made of small molecules. Mark number 2, you say that there are weak intermolecular forces between these molecules. This is so important you have to use the phrase intermolecular forces, not covalent bonds. And finally, mark number 3, because those forces are weak, it takes very little energy to overcome them. That's it, 3 clear points, 3 marks in the bag. Okay, let's switch gears. We're moving away from the concepts and into the calculations. Time to crunch some numbers.
First up, a quick 1-marker. Question 05.4 asks us to pick the catalyst out from a list. The mark scheme confirms the right answer is Cr2O3, which is chromium oxide.
Okay, now for the main event of this section, question 5.5. We've been given the reaction equation with all the bonds drawn out, and a table full of bond energies. We have absolutely everything we need to figure out the overall energy change.
The trick here is just to be systematic. So, step 1, calculate the energy in. This is the energy needed to break all the bonds in the reactants. We have 4 ammonia molecules, and each one has 3 NH bonds, so that's 12 NH bonds. We also have 3 O equals O double bonds. Using the table, that's 12 times 391 plus 3 times 498, giving us a total of 6166 kilojoules. Step 2, calculate the energy out. This is the energy released when we make new bonds in the products. That's 2 N triple bonds and 12 OH bonds. Using the table again, that's 2 times 945 plus 12 times 464, which gives us a total of 7458 kilojoules. Now for the final step, you just subtract the out from the in.
And that brings us to our final answer for 3 full marks, negative 1272 kilojoules. And you've got to pay attention to that negative sign. It's super important for the very next question.
So question 05.6 asks us to explain why the reaction is exothermic, using the numbers we just calculated. And this right here is the perfect answer. The reaction is exothermic because more energy is released when we make the new bonds, 7,458 kilojoules, than the energy that was absorbed to break the old bonds, 6,186 kilojoules. That extra energy gets released out into the surroundings.
All right, we're on the home stretch. Let's tackle the last part of question 05. We've done the calculation, and now we get to see what it actually looks like.
For our last 2 marks, we need to correctly label a reaction profile diagram. There are 2 key things to identify: the activation energy and the overall energy change.
And here is the perfectly labeled diagram. The activation energy is that hump you have to get over. It's the energy needed to kickstart the reaction, measured from where the reactants start to the very peak. And the overall energy change, that's just the difference between the starting energy of the reactants and the final energy of the products. And see how the products are at a lower energy level? That's our visual proof that this reaction is, just like we calculated, exothermic.
And that's it, the entire question, start to finish. So let's take a quick moment to recap what we've just covered and pull out the big lessons here.
I mean, just look at the range of topics that were packed into this one single question. We tackled dot and cross diagrams. We explained physical properties using intermolecular forces. We nailed a multi-step energy calculation, and we interpreted a reaction profile. It really shows you how all these core ideas in chemistry are truly woven together.
And that really brings us to the most important point of all. We didn't just answer a chemistry question today. We learned how to read the mind of the examiner. Understanding how marks are given is just as crucial as knowing the science. So when you're revising, don't just do practice questions. Take the time to dissect the mark schemes, because that is how you turn a good answer into a perfect full mark answer.